Well, let's start off with something different. Some years ago, I saw at a meeting where I was attending a neat little chemical reaction that was initiated by ultraviolet light. The reaction is given here in this equation. H2 plus Cl2 goes to 2HCl. If you combine equal molar quantities of H2 and Cl2 and you put them in a test tube with a cork, nothing happens. Okay? They just sit there. Even though this reaction, under some circumstances, is almost explosive, these two gases don't do a thing unless you provide a source of ultraviolet light. And what's done here, hang on, you're getting ahead of me. What's done here is to take a piece of magnesium ribbon, set it afire, and there is a hole in the side of the cannon here. And you put the tube in the cannon, then there's a hole where the ultraviolet light can go in. You're not going to hear this unless I turn up the volume. Be prepared to get blasted here. I don't know how loud this is going to be. Okay, so what's going to happen is the tube is going to be placed in the cannon here. The magnesium ribbon will be burned, and the very bright light from the magnesium ribbon, it's used to make flares and things, will initiate the reaction, and you will have to watch to see what happens.
They have been placed into a test tube with a cork in it. The test tube is placed into a small cannon with a hole in the side that will allow light to pass through. The magnesium ribbon is ignited and brought close to the hole, and when the light from the burning magnesium ribbon strikes the mixture, the hydrogen and chlorine react explosively, propelling the cork out of the test tube. The test tube is placed within the brass cannon for safety. Should the explosion shatter the test tube, the metal would prevent flying glass.
Instant replay. We didn't see that first one.
The hydrogen and chlorine do not react when they are just mixed together, but the reaction can be initiated by a bright light.
Okay, so we maybe buy that ultraviolet light could initiate a reaction. We don't know enough about it at this point to be sure, but it doesn't sound entirely unreasonable. But even given the fact that the reaction goes, why does the cork pop out of the tube? Well, let's think about this a minute. Let's suppose the reason the cork pops out of the tube is the pressure gets larger. So if we look at this mixture of gases as an ideal gas, P is equal to nRT over B. Well, the number of moles of gas don't change. There are 2 on the left and 2 on the right. So it's not due to a mole change. The volume doesn't change, the volume of the test tube. And so what else could cause the pressure to increase? The temperature. The temperature could cause the pressure to increase, but where would the higher temperature come from? Reaction. Well, the ultraviolet might add a little bit to it, but you probably saw that reaction went off just about as soon as even a little bit of ultraviolet light was on there. It's something else. It's this reaction. This reaction evidently releases heat, which causes the temperature to go up. And when the temperature goes up, the pressure goes up, and the cork goes across the room. So what we have here, something later on we will call an exothermic reaction. Okay? It is a reaction that the products are more stable thermally than the reactants, and the difference in energy is released and makes the cork go across the room. So maybe the temperature increases during the reaction that would increase the pressure. So that's why we've talked about it. So I want to talk, in order to evaluate whether that's a possibility, I want to be sure that everybody is comfortable with the idea of how energy is related to systems, reactants, products, bricks, and all kinds of things here. And the first thing we need to do is to recognize that any given thing that we might study has associated with it, if it's an object, a potential energy, which is usually by virtue of its position or its chemical bonds, and a kinetic energy, which is almost always due to its motion and maybe its mass. So if we had a brick up on the ceiling and somebody wanted to conk me with it, they could drop it down, and if their aim was real good, they might hit me, or they might hit the floor with the brick. Okay? That's never happened yet. But in principle, it could happen. So the brick being up on the ceiling has very high potential energy due to its position in the gravitational field of the Earth. And so if you let go of it, it will be attracted to the Earth by gravitational attraction, and it will fall until it encounters something. The potential energy that it had up there gets converted to kinetic energy. When it hits the ground, or my head, it transfers some of its kinetic energy, which is considerable by now. Remember, 1/2 mv squared. As the velocity builds up, kinetic energy will build up very fast. And it will transfer some of that kinetic energy to whatever it hits. Okay? And if it hit dirt, it would move some of the particles of dirt, and we say it would do work on the dirt particles, or my head, as the case might be. And some of that work would end up being the part of the amount of energy that it took to raise that brick up to the ceiling. Okay, so we sort of put energy into the brick by raising it up. Then it comes down, and that energy gets converted from potential to kinetic, and then there's a collision at the bottom, and then some of the kinetic energy gets converted to kinetic energy of something else, and maybe some of it would heat up, would cause the temperature to rise. There are lots of different things that might happen in a complicated case like a brick. Something we understand a little bit better than brick is the energy in chemical bonds. Probably when you got up this morning, if you had breakfast, maybe you ate a piece of toast, in order to have a little bit of energy to make it through the traffic to school and listen to Geanangel talk about energy. Okay? That piece of toast would undergo a reaction in your body, which we call metabolism, and in the process, some of the stored energy in the molecules of the toast would be released. Okay? And the same thing is true with the fuel that we might have used if we drove our cars to school or to somewhere else. And in both of these cases, the potential energy of the chemical bonds in the food and the fuel is converted partly to kinetic energy. I say partly because the process, particularly in driving a car, is not very efficient. We don't manage to convert very much percentage-wise of that energy driving the car because of the machinations that we use to convert the heat produced by the fuel into kinetic energy. That was a little bit too quick. So whenever energy is transferred from one object to another, it appears either as work, W, or heat, Q, or both. It doesn't get lost. And for almost all the cases that we might encounter in this course, there'll be some combination of W and Q. So we need to talk about those. And in order to do that, we need to define what the system is, literally. If we're talking about the energy flowing out of a gallon of gasoline, the system is the gallon of gasoline and how much air we needed to burn that gallon of gasoline. That would be one way to define it. Energy in the process might be released in order to help drive our car. So the change in energy is defined as the energy difference between the final state, CO2 and water vapor, and the initial state. So we would have to pick a system, which would be that part of the universe whose change is to be measured, and the sum of the kinetic energy and potential energy of all the particles in the system. Think about a gallon of gasoline and however many moles of air are needed to burn it. And the sum of the kinetic and potential energy of them is equal to its so-called internal energy. Sometimes that's called E, sometimes it's called U, depending on who wrote the textbook. The internal energy is something that we talk about, but we rarely measure. I think I'll show you only one example of where we look at the internal energy of a system. Most of the time, we're interested in the change in the internal energy. So as a chemical system goes from reactants to products, the internal energy changes because the internal energy of the reactants, all of those octane molecules and oxygen molecules, is going to be different than the internal energy of all the products, which are CO2 molecules and water molecules. Okay, so the internal energy of the system will change, and what we're focusing on is by how much. So delta E for our system in a chemical reaction is defined as E of the final state minus E of the initial state. That's the thermodynamic definition, if you will, for delta E. The thermodynamic thermodynamic definition. E final minus E initial. In terms of the chemical reaction, it's simple. E of the products minus E of the reactants. The final state minus the initial state. The energy change then appears as heat and or work, and we express it with this equation, which you better not walk out of this room without knowing. Okay? You're going to need it. Delta E, the change in internal energy, is equal to Q, the heat change, plus W, the work done. Okay, so what I'm going to do here is I'm going to show you how a chemical system can change its internal energy. One way that it can do that is to lose some energy to the surroundings. If we take an undefined chemical system that loses energy to its surrounding, this might be the gasoline and oxygen, for example. It's at a certain state, and then we use it to drive our car, however far we can get it for a mile. And the initial state is changed to the final state, and energy is lost to the surroundings. Why is that? Well, you've got to move the car, for one thing. It takes energy to move the car. Secondly, that engine gets hot. It takes energy to get the engine hot. The hot engine heats the air. It takes energy to heat the air. Heats the water in the radiator, all that good stuff. So if energy is lost to the surroundings, like it surely would be in your car engine, then the final state of your system has an energy, E final, which is less than the initial state's energy, E initial. Okay? We would look at this thing, delta E would be this number, a smaller number, minus that number. So delta E is less than 0 because E final is less than E initial on the energy scale. Does it make sense? So that's one way it can do. Another way is it could change its internal energy by getting some energy from the surroundings. If that's the case, the initial state is down here on the energy scale, and the final state is up here by a larger amount. Some energy came in from the surroundings and was added to the system, making its final energy greater than the initial energy. So E final is greater than E initial, so delta E in that case will be greater than 0. The internal energy increases by an amount equal to the energy coming in from the outside. So again, delta E is equal to E final minus E initial. And if this is a chemical reaction, which represents the change, it's E products minus E reactants. Now, if the energy enters or leaves the system as heat or work, we could have, at least hypothetically, a situation where the system does no work but transfers energy as heat. If you've had physics, you already know. If you've had mechanics, that work is usually defined as exerting a force on something of a certain mass and moving it by a certain amount. That's usually roughly how they define it. But let's suppose no work is done, but heat is exchanged. So if work is 0 and delta E is equal to Q plus W, then delta E is equal to Q. All right? Let's suppose that this particular scenario is a cup of hot water or hot coffee or hot tea, something is put on the desk here. Initially, T of the system is greater than T of the surroundings. But if it's sitting here and it's not perfectly insulated, its higher temperature will mean that energy will be transferred to the surroundings, and the energy going into the surroundings might cause the temperature of the surroundings to increase slowly. In other words, if it's sitting, if the hot water is sitting here on the bench, after it's been there a little bit, the air in the immediate surroundings will be warmer, and the bench will be warmer right where it is. So Q, some amount of heat is lost in the surroundings. That amount of heat is in fact gone from the internal energy of the system as we initially defined it. So Q is less than 0. And if delta E is equal to Q, because W is 0, then delta E is less than 0. And this process will continue until the temperature of the system is exactly equal to the temperature of the surroundings. Then heat flow will stop. Things will be stable. Thermodynamics and thermochemistry are concerned with the changes that occur in the internal energy of chemical systems. And so we tend to focus mostly on chemical reactions. Reactants going to products. And we had defined the change in internal energy in those kinds of systems as Q plus W, where Q is the heat change and W is work done either by the system or on the system. Q could be heat released by the system or absorbed by the system. And we had just begun talking about a hypothetical system that is made up of an insulated container with an attachment to a piston cylinder apparatus, the outside of which is exposed to the atmosphere. And it's made up of zinc and hydrochloric acid. Those are the reactants for this particular reaction. And we are concerned with what happens when the reaction takes place and it produces zinc chloride and hydrogen. I trust that you can write a balanced chemical equation for that, but I'm going to focus only on the hydrogen gas that's produced. The hydrogen gas will increase the pressure inside the system, and it will push back on the piston and move the piston against the pressure of the atmosphere. That is equivalent to doing work on the atmosphere. Pushing back the atmosphere is work done by the system on the atmosphere. So what that means is that amount of energy equivalent to that work is lost to the system. So delta E, the change of internal energy of the system, is going to be negative under those circumstances. Now, I remind you, this is a hypothetical case. Okay? So if Q is 0, no energy, no heat energy is lost or gained in this hypothetical case, delta E must be equal to W. And if W is negative, then delta E will be negative as well, since delta E is equal to W. So when work is done by a system on the surroundings, if nothing else happens, delta E becomes smaller. There's less internal energy left in the system. If we look at the work done, when work is done by pushing back on the atmosphere, like it is in this case, that's called PV work. And when the atmospheric pressure remains constant, which we usually assume that it does, the amount of that work is given by a special equation. It's equal to minus the pressure times the change in volume. The change in volume would be the initial volume, or the final volume of the system, minus the initial volume of the system. And if P is in atmospheres, delta V will be in liters, and the term, which we'll come back to a little bit later today, the work in that case is defined in units of liter atmospheres. Okay, and this equation only works when the pressure is constant. So if we took this final situation that we had here and we increase the external pressure by some magical way that we had, we could then do work on the system and push the piston back down to where it was. If we did that, doing work on the system, that would mean that the change in internal energy for that process would be greater than 0. The internal energy of the system would be increased by the work done on it. So W would be greater than 0. So now we have kind of a working description of the importance of the signs of Q and W. And it's summarized here. If Q and W are both positive, it means delta E must be positive. If Q and W are both negative, then delta E is negative. If Q is positive and W is negative, or Q is negative and W is positive, then the overall effect on delta E depends on the relative sizes of Q and W, obviously. Important thing to take home with you out of this slide. For Q, a positive side sign means the system gains heat. A negative sign means the system loses heat. For W, a positive sign means work is done on the system by something in the surroundings. And negative means it's work done by the system on the surroundings. Now, what are the units of this internal energy? The international unit is the joule, or if you grew up in the British Isles, they mostly pronounce this joule, but joule, I think, is universally accepted here. And 1 joule is defined in the international system as a kilogram meter squared per second squared. This is mechanics and physics kind of definition for it. We will use joules for describing both heat and work changes. Okay? Now, you have heard, of course, about the calorie. And from time to time we'll talk about calories, since they are kind of a common way to express energy and work. This is based on the British system. A calorie of energy is needed to raise the temperature of 1 gram of water by 1 Celsius degree. And the relationship between the joule that we're going to use and the calories that you might have used in high school, I don't know, is here. The calorie is a little over 4 times larger than the joule. And if you run across problems in calories, it's convenient and helpful to remember this relationship. 4.184 is going to come up so many times. I think you'll remember it whether you want to or not. So we'll go along with that. Energy changes in chemical reactions are typically much larger than joules. So we normally will give the energy changes for that situation in kilojoules. And of course, 1 kilojoule is just 1,000 joules, or about 0.24 kilocalories. Okay, so those are the units and those are the signs. What I would like to do now is to talk about the overriding relationship that controls Q and W. We gave the equation delta E equals Q plus W at some point, and I just want to point out to you that this is a zero-sum game. If we define a system and it gains energy, that, whether it's Q or W or some combination, the surroundings must lose an equivalent amount. You can't create energy, nor can you destroy energy. You could convert it from one form to another. That's about all you can do to it. So the law of conservation of energy expresses this, that if a system gains, the surroundings must lose, and vice versa. Another way to say this is that the total energy of the universe is constant. Okay? And another way to say that is that the internal energy of the system plus the internal energy of the surroundings is a big constant. Okay? Or energy is conserved. So sometimes you'll see this written out as delta E of the universe is equal to delta E of the system plus delta E of the surroundings. And since the magnitudes of these two things are the same for any change that we might want to talk about in the system, only the signs are different. The two numbers, one will be plus and one will be minus, and the value will be the same. So delta E of the universe is equal to 0. So all of those things are used to illustrate the principle of the law of conservation of energy. All right, one of our focuses will be to figure out what delta E is for a given change. So I have here a problem that I want to offer you about calculating delta E. Most of the time we're going to be focusing on delta E rather than E, although I will show you one example where we'll look at E itself. Let's suppose that we're talking about a student who has a CD player. There's probably nobody in here that even has a CD player. You all have iPods, don't you? Mostly likely. Well, a CD player used to have a battery and a motor that spun the CD so you could listen to the music. There might be somebody around. If you're old enough, you might have one of these. Okay? So let's suppose that a student was playing music on her CD player, and during that process, the battery in the CD player, supplied the energy for this system, does 250 joules of work spinning the CD, running the motor. And during that process, the battery gets warm. It being a higher temperature than the surroundings, it loses 35 joules of heat in that same time period that it did 250 joules of work. So given that scenario, we need to calculate delta E for the battery and then for the surroundings. The battery then becomes the system, and if the system is the battery, then delta E of the battery is equal to Q of the battery plus W of the battery. And we have seen pretty clearly that the heat released here, the heat is released because the battery got warm, and so Q of the battery will represent heat going from the system, the battery, to the surroundings, and so Q will be negative. And the work is done by the battery on the surroundings, specifically the spinning the CD, and so what we have here is the sign, an indication of the signs of Q battery and W battery. Q of the battery will be equal to, this is the heat change, it'll be 35 joules, and it's heat that's lost, so that's minus 35 joules. And W of the battery is equal to 250 joules, and it was done by the battery, the system, on the surroundings, so it's energy lost to the internal energy of the battery. So this is minus 250 joules. Okay? So what we'd like to do now is to calculate delta E of the system and delta E of the surroundings. So we'll take delta E of the system first. So delta E of the battery is equal to Q of the battery plus W of the battery. And given the numbers up here, that's minus 35 joules minus 250 joules. And that boils down to minus 285 joules. So the internal energy of the battery decreased by 285 joules. Now the surroundings were the recipient of that energy, both Q and W. So by the law of conservation of energy, delta E of the surroundings will be equal to minus delta E of the battery. So that's minus a minus 285 joules, or of course that's positive 285 joules. All the energy lost by the systems gained by the surroundings. Questions? Q plus W. Very simple, easy to use if you remember the signs. Any questions about it? Okay. Let's do a more chemically oriented one of these, or maybe it is. Let's look at this one. Now we have a piston cylinder arrangement, and it's got helium gas in it, and the amount of the helium gas and the conditions are such is at the beginning, this helium gas is our system, and it has an internal energy of 1,500 joules, whatever it is. Let's just say it's 1,500 joules. A change occurs whereby the gas, which is our system, receives 525 joules of heat. So Q represents energy going into the system here. That's the reason for my little arrow right there. And the magnitude is 525 joules, and the sign is positive because the heat is added to the system. At the same time, the piston slides back against the atmosphere and does work against the atmosphere, and the magnitude of the work is 428 joules of work exerted by the system, which is the gas, on the surroundings. What is the final internal energy of the gas? Okay, so we know what Q is, we know what W is, so we can calculate Q plus W, which of course is delta E, and we can put in Q and W for that. That's plus 525 joules for Q, and minus 428 joules for W. And the difference is plus 97 joules for delta E. Okay, so the gas internal energy increased by 97 joules. And up here we have delta E is equal to E final minus E initial. E initial was given in the problem at 1,500, so 97 joules, delta E is equal to E final minus 1,500. We solve for E final, and of course it's 1,597 joules. Questions on delta E equals Q plus W? Yes, go ahead.
The energy release, is that in piston heat or then water loss?
I'm sorry, the energy released is...
Whenever you lose energy, or say you lose like 400 joules,
It can either be Q or W or some combination of them. In other words, if the system has higher temperature than the surroundings, it's going to, without doubt, lose some energy as heat. But if it's an expanding gas and has to push back the atmosphere, it's going to do some work. So this minus 428 joules right here is work, W. but it could be, you know, either Q or W or both.
Well, say it's doing work, would the temperature increase? Is there anything that's chemically different about the gases?
You're asking if by doing work I imply that there's a temperature increase. There may or may not be, but my point is it doesn't matter. If W has this magnitude and it represents a pushing back of the atmosphere, the sign has to be negative. We don't really have to worry about whether the temperature changes or not with W. PV work just assumes that we have constant pressure. That's all it assumes. Did I get your questions? Delta T could be, a change in temperature could be the reason why the gas expanded. Certainly could be. And in this case where we put heat in, one would expect it. But it's not required. We could have a chemical reaction in which the number of moles of gas changed in such a way as to make the pressure go up and push back the atmosphere. Okay. Delta E does not depend on how specifically a change takes place. It only depends on the initial and final states of the system. Because of that, it is called a state function. Depends on the initial and final states. If we look at a chemical system that consisted of 1 mole of octane and enough oxygen to burn that octane, the reactants would be octane and oxygen. The products would be CO2 and water. And here's a balanced chemical equation for that process. Now, if we burned 1 mole of octane with 12.5 moles of oxygen and got 8 moles of CO2 and 9 moles of H2O, that would produce a certain amount of heat. How do I know it would? Well, it's a combustion. I know from personal experience that combustions always produce heat. I've never met one who didn't. Okay? So, if it produces heat, then we can make an energy diagram like this. Energy is increasing this way. Here's 1 mole of octane plus 12.5 moles of O2. This is at the initial energy of the system. Now, if I carried out that process, unless I was able to do it under very peculiar conditions where no heat was lost and no work was done, I would expect a substantial amount of heat to be lost to the surrounding. How do I know that? Well, octane is one of the main components of gasoline. So if I put a mole of octane in the engine of my car and went down the street until I ran out, I would know the engine's going to get hot. Right? If I put my hand on it, I'll be able to tell. It's pretty hot. I'll also know that during the process, these gases push back the atmosphere. So if I burn 1 mole of octane in the automobile engine, some heat is lost and some work is done. And we go from this initial state up here down to that final state right there. And delta E would be equal to Q plus W. Now, if on the other hand, we just took that mole of octane, put it in a barrel and burned it, it wouldn't do any mechanical work for us. It's true it would push back the atmosphere somewhat because more moles of gas are produced than were used here. But most of the heat, most of the energy change would be lost as heat. Now the point is that delta E is the same in both of these cases. E final minus E initial. The point that I want to make is that Q and W won't necessarily be the same if we have a different pathway here. So some energy from the fuel heats and or does work on the surroundings, so delta E is negative. We go down the hill here. And the magnitude will be determined by the internal energy of the final set, which is of products here, 8 CO2s and 9 H2Os under whatever conditions they are, minus the energy, the internal energy of the initial reactants here. So delta E is the same for both paths, but Q and W can vary depending on how we actually carry this out. So internal energy is a state function. It is a property which is determined only by the current state, and a change in internal energy is only determined by the final state and the initial state. Okay. As a general observation, not only is delta E a state function, but so also is delta P, the change in the pressure, if any, and delta V, the change in the volume, if any. All of these depend only on the initial and final state, not on the pathway. Q and W are not state functions because they depend on the pathway, as we saw with the automobile engine and the barrel.